Welcome! In this lesson, we will build intuition for three model types used to simulate growing mountain belts: finite element, finite difference, and cellular automata. We will see how each method discretizes space, what it does well, and where it struggles. First, a quick visual of numerical discretization ideas you will encounter. Top left shows a quad-tree mesh with local refinement for places that need detail. Top right shows triangular elements that can hug curved boundaries. Bottom left shows particle in cell material tracking, with two material types moving through a grid. Bottom right shows how interfaces can be represented as sharp or smoothed fields on a grid. Now, let's look at each model type in more detail. Finite element method. FEM subdivides space into elements and represents unknown fields with shape functions. It excels with complex geometries like curved topography or even spherical shells. We can impose boundary conditions cleanly and combine physics like elasticity, heat, and fluids. We assemble a global matrix, often written as Ku equals F, and solve for the unknowns. Popular tools include PYLith for crustal deformation and COMSOL or Abacus for multiphysics. The trade-off is setup complexity and computational cost in 3D. Finite difference method. FDM lays a regular grid and replaces derivatives by differences between neighbors. It is straightforward and fast for simple geometries. Curved interfaces on a rectangular grid can stair-step unless special coordinates are used. Here is a 5-point stencil for the Laplacian. Explicit time marching updates the state. U at n plus 1 equals U at n plus delta t times the operator. FLAC is a classic grid-based code used for fold and fault evolution with large strains. Cellular automata. CA uses a grid of cells with local update rules to mimic processes like erosion, landslides, and sediment transport. It captures threshold behavior and emergent patterns. Here is a simple rule. If local slope exceeds a threshold, move one grain downslope. Events can happen asynchronously at different rates, avoiding a global time step. LandLab includes cellular automata components for landscape evolution, and Caesar Lease flood models river morphodynamics. How to choose. Use finite elements when boundaries are complex and coupling multiple physics matters. Use finite differences for simpler domains, fast prototyping, or explicit dynamics with large strains. Use cellular automata to explore threshold processes and emergent landscape patterns. Modern studies often couple methods, for example, finite elements for stress with a surface process module that is finite difference or cellular automata based. Balance accuracy, complexity, and computational cost to answer your scientific question.